On August 9th, 2026, an asteroid measuring roughly 756 meters across, wider than most skyscrapers are tall, swept past Earth at a distance of about 5 million kilometers. Picture that object the way NASA's own tracking software renders it. A small, dark dot moving steadily across an interactive orbital map, a thin white line tracing its path safely past a blue marble representing Earth, close enough on a cosmic scale to warrant careful tracking, far enough in absolute terms that the two paths never come close to intersecting. NASA had been tracking it for months. It carries an official label most people will never see, potentially hazardous. That single classification, attached to an object large enough to end civilization if it ever struck land, is exactly the kind of phrase built to catch attention and then immediately raise a harder question. Should anyone actually be worried? This is the story of asteroid 2000 YV-137, what potentially hazardous genuinely means when NASA uses it, and why. The honest answer to whether we should be worried is both reassuring and, in its own way, a lot more interesting than a simple yes or no. To understand why an asteroid passing 5 million kilometers away, more than 12 times farther out than the Moon, still earns a label as serious sounding as potentially hazardous, you first need to understand exactly how that classification actually works, because the term gets thrown around far more loosely in headlines than it does inside NASA's own tracking systems. An object qualifies as a potentially hazardous asteroid based on two specific, purely mechanical criteria, nothing to do with any current predicted collision. First, its size has to exceed roughly 150 meters in diameter, large enough that, in the extremely unlikely event it ever did strike Earth, the resulting damage would extend well beyond a single city and could plausibly affect an entire region, or more, releasing energy on a scale measured in hundreds of megatons rather than the kilotons associated with smaller, more localized impacts. Second, its orbit has to bring it within 7.5 million kilometers of Earth's own orbital path at some point, close enough, on cosmic scales, that its trajectory needs continuous monitoring and refinement rather than a one-time calculation filed away and forgotten. A threshold set deliberately wide to catch anything worth double-checking, rather. Then narrowly around only the most extreme immediate concerns. Asteroid 2000 YV-137 meters across and passing within about 5 million kilometers, which is exactly why it earned the classification. Nothing about that label implies NASA expects it to actually hit Earth, now or at any point in the foreseeable future. It's closer to a permanent watch list entry than an active warning, the astronomical equivalent of a building being labeled as sitting in a flood zone on a map, a designation describing its general risk category based on location and size, not an announcement that flooding is actually happening or imminent. That distinction matters enormously, and it's worth sitting with for a moment, because it's precisely the gap where headlines tend to manufacture drama that the underlying science doesn't actually support. NASA's Center for Near-Earth Object Studies, the division responsible for tracking objects exactly like this one, has been explicit and consistent. The 2026 passage of 2000 YV-137 carries no collision risk whatsoever. 5 million kilometers is a genuinely enormous distance by any everyday standard, more than 13 times farther than the Moon orbits Earth, a gap so large that even a meaningful error in the asteroid's calculated trajectory would leave an enormous margin of safety several times over. The potentially hazardous label describes the asteroid's general category, based on its size and orbital proximity as a type of object, not a specific active threat assessment for this particular flyby, a nuance that rarely survives the trip from a scientific database into a headline built to generate clicks rather than convey precise risk. To understand how NASA actually distinguishes a routine, harmless flyby like this one from a genuine cause for concern, it helps to know about the tool built specifically for that purpose, a monitoring system called Sentry. Every time astronomers that couldn't discover a new near-Earth object or gather additional observations refining an already known one's orbit, that data feeds automatically into Sentry, which runs continuous calculations projecting each object's trajectory decades, sometimes even a full century, into the future, essentially running an enormous, constantly updating simulation of the entire solar system's known small body population. For the overwhelming majority of tracked objects, those calculations converge quickly on an extremely confident, extremely safe trajectory with any theoretical impact. Probability dropping to numbers so small they might as well be zero for any practical purpose, often expressed in scientific notation with more zeros after the decimal point than most people would ever bother counting. Only a small handful of objects out of the many thousands NASA currently tracks ever register even a non-zero, statistically noteworthy impact probability worth publicly flagging. And even those cases typically involve probabilities measured in fractions of a percent, spread across possible impact. Dates decades or even a century away, numbers that shrink further, almost without exception, as additional observations refine the object's known orbit over time. There's a well-known, genuinely instructive case study that shows exactly how that refinement process plays out in practice. The asteroid Apophis, once considered one of the more concerning objects NASA had ever tracked. When first discovered in 2004, early calculations suggested a genuinely unsettling possibility, a roughly 2.7% chance that Apophis could strike Earth during a close pass in 2029, a number small in absolute terms but startlingly high by the standards of asteroid risk assessment, high enough to briefly push the object to the top of international risk monitoring lists and generate real headlines and real concern at the time, with some outlets speculating openly about what an impact from an object of that size might actually mean for the region unlucky enough to be underneath it. Then, as astronomers gathered more observations and refined the asteroid's orbit with greater precision, that risk didn't just shrink, it eventually vanished entirely. By the end of 2004, a newly recovered image extending the observation history further back in time, essentially finding an earlier, previously overlooked photograph of the same object taken months before its official discovery, let researchers rule out any 2029 impact altogether. A smaller, more technical worry lingered for a few more years, the possibility that Apophis might pass through an extremely narrow, specific region of space during its 2029 flyby, a so-called gravitational keyhole less than a kilometer wide, that could have set up a delayed impact exactly 7 years later in 2036. Continued tracking eventually ruled out that scenario too, and by 2021, NASA had formally removed Apophis from any impact risk list entirely for at least the next century, closing the book on an object that had once briefly represented one of the more serious concerns in the entire field. That case is worth understanding in detail because it captures the actual rhythm of how asteroid risk assessment genuinely works, a rhythm that rarely matches the tone of the headlines built around it. New discoveries, and especially objects with only a short observational history, often carry more uncertainty in their calculated orbits, uncertainty that can occasionally translate into an initial non-zero impact probability worth flagging publicly and monitoring closely, almost without exception, as astronomers gather more data tracking the object across additional nights, months, or in some cases years. That uncertainty shrinks and the calculated risk drops along with it, typically down to zero or some infinitesimally small number well before the object's predicted close approach actually arrives. Genuine, sustained, high probability impact warnings, the kind that would actually justify serious public alarm, are exceptionally rare, and history strongly suggests that any object currently generating that level of concern would almost certainly see its risk. Assessment improve, not worsen, as additional tracking data comes in. None of that means asteroid monitoring itself is some kind of overblown, unnecessary exercise, and it's worth being clear about why the opposite is actually true. The entire reason initial risk assessments can start out uncertain, and the entire reason systems like Sentry exist and run continuously in the background, is that genuinely dangerous impacts, however statistically rare, remain physically possible, and the only real defense against one is early, sustained detection. Earth's history carries direct physical evidence of exactly what a larger impact can do. The Chicxulub impact, roughly 66 million years ago, involved an asteroid estimated at somewhere between 10 and 15 kilometers across, an object dramatically larger than 2000 YV-137, striking what's now the Yucatan Peninsula in Mexico, with enough force to trigger global wildfires, blot out sunlight with debris thrown into the atmosphere, and collapse food chains across the entire planet. Effects that reshaped Earth's entire climate and ended the age of dinosaurs within a geologically instantaneous span of time. Much smaller, far more common impacts still carry real demonstrated consequences on human timescales, closer to the kind of event any of us might actually witness in a single lifetime. The 2013 Chelyabinsk event, caused by an object only about 20 meters across, far smaller than the 150-meter threshold that even qualifies something as potentially hazardous, entered the atmosphere at an extremely shallow angle over Russia, releasing energy equivalent to roughly 500,000 tons of TNT as it broke apart in a brilliant, sky-spanning fireball caught on hundreds of dashboard cameras across the region, shattering windows and injuring more than 1,500 people, almost entirely from flying glass rather than any direct impact. A sharp reminder that even objects too small to earn NASA's more serious classification can still cause genuine, if localized, damage arriving, with essentially no public warning at all, since an object that size is extraordinarily difficult to detect before it's already close enough to matter. That range, from a relatively small atmosphere-shattering object like the one over Chelyabinsk, up through civilization-altering impactors on the scale of Chicxulub, is exactly why size thresholds like the 150-meter cutoff for potentially hazardous Stat 2 around the point where an impact's consequences would plausibly extend beyond a single region into something requiring serious, coordinated global concern. An object the size of 2000 YV-137 at 756 meters sits well above that threshold, large enough that a genuine impact, however astronomically unlikely, would represent a serious, continent-scale event rather than a localized one. That's precisely why its category matters, and precisely why NASA continues tracking it and every other object like it, even while confirming, with high confidence, that this particular 2026 flyby poses no actual risk. It's worth understanding, too, just how much of modern planetary defense infrastructure exists specifically to keep pushing that detection net wider and further out, catching objects earlier and with more lead time than previous generations of survey telescopes ever could. Dedicated asteroid hunting observatories, cataloging thousands of new near-Earth objects every year, have dramatically improved humanity's collective ability to spot potentially hazardous asteroids years or even decades before any close approach, giving scientists, and if it ever became necessary, engineers, far more lead time to refine an object's trajectory, or in a genuine worst-case scenario, attempt some kind of deflection mission. The kind of concept NASA's own DART mission successfully demonstrated was physically achievable back in 2022, when a spacecraft deliberately collided with a small asteroid moonlet called Dimorphos and measurably altered its orbit around its larger companion asteroid, shortening its orbital period by more than half an hour, a far larger shift than mission planners had even dared to hope for going in. That result proved, for the first time in human history, that a deliberate, targeted impact could meaningfully change an asteroid's path using nothing more exotic than the kinetic energy of a spacecraft slamming into it at high speed. A genuine proof of concept for a technology nobody had ever needed to actually test in real conditions before. None of that technology and infrastructure exists because scientists expect an imminent catastrophe. It exists precisely because the stakes of being wrong, of missing a genuinely dangerous object simply because nobody was looking closely enough, are high enough to justify decades of careful, patient, largely uneventful monitoring, the kind of quiet, unglamorous insurance policy that only makes headlines on the rare occasions it reveals something the system was specifically built to catch. So here's an honest answer to the question this specific asteroid's own headline keeps asking. Should anyone be worried about 2000 YV-137's August 2026 passage? No, not in any meaningful sense. NASA's own tracking data places it safely, confidently 5 million kilometers away, well outside any realistic collision scenario, confirmed by the same rigorous, continuously updated modeling system that has correctly walked back every other initially concerning near-Earth object, including Apophis, as additional data came in. What's actually worth appreciating about this story isn't danger. It's the quiet, unglamorous competence of a global tracking system working exactly as intended, cataloging an object more than 700 meters across, calculating its path with enough precision to confidently rule out any threat months in advance, and doing so as one routine entry among thousands of similar objects currently being tracked at any given moment, each one running through the exact same rigorous, continuously updated calculations, regardless of how much or how little public attention it happens to attract. That routine competence is easy to overlook precisely because it works. Nobody writes headlines about asteroids that were tracked accurately and confirmed harmless years in advance, even though that outcome represents the overwhelming majority of every near-Earth object ever discovered, a genuine, if unglamorous, success story repeated thousands of times over without ever generating the same attention as a single, scary-sounding classification. The headlines that do spread tend to seize on the scarier-sounding classification, potentially hazardous, without following through to the actual reassuring context that classification exists within, stripping away exactly the nuance that would turn an alarming-sounding phrase into an accurate, calm description of a well-understood, well-monitored object. Understanding that distinction between a category describing an object's physical characteristics and an active, specific threat assessment is really the single most useful thing anyone can take. Away from a story like this one, applicable not just to 2000 YV-137, but to every future asteroid headline that will inevitably follow the same basic pattern in the years ahead, recycling the same dramatic-sounding label attached to a new set of numbers and a new object, with the underlying reassurance almost always buried somewhere further down in the actual data. It's worth putting a number on just how many objects this entire system is quietly managing at any given time, because the scale of it is easy to underestimate. NASA's Center for Near-Earth Object Studies currently tracks well over 30,000 known near-Earth objects, with new discoveries added to that catalog on a near-daily basis as survey telescopes continue. scanning the sky night after night. Of those tens of thousands of tracked objects, only a small fraction carry the potentially hazardous designation, and of that smaller group, essentially none currently carry any meaningful non-negligible impact probability for the foreseeable future. Every single one of those tens of thousands of objects runs through the same Sentry calculations, the same continuous refinement process, the same rigorous scrutiny that eventually cleared Apophis and that has already cleared 2000 DARS YV-137, a genuinely enormous ongoing bookkeeping effort that rarely gets any public attention, specifically because it keeps working. So somewhere out past the moon's orbit right now, 2000 YV-137 continues along its own long, well-mapped path around the sun, one of thousands of objects NASA's tracking systems currently monitor with quiet, continuous precision. It will keep returning periodically, its orbit refined a little further with each new observation, its risk assessment already effectively zero, growing only more confidently zero with time. That's not a disappointing ending to a space story. It's the ending every properly functioning planetary defense system is actually built to produce, again and again, one carefully tracked, safely passing asteroid at a time, a quiet, repeating success story playing out largely unnoticed, precisely because it keeps ending exactly the way it's supposed to,